Hey everybody, this is lesson 4.6b. It's more on related rates. Sometimes more than two quantities are changing within a certain relationship. At this point, you must consider the product rule, the quotient rule, and the chain rule when differentiating to express how different rates of change are related. Okay, so we'll start off with some area formulas. First of all, the area of a rectangle is length times width. Find an equation that relates dA dt, dL dt, and dW dt. Okay, so notice that length times width, that's a product. So we'll have to incorporate the product rule, where you do the derivative of the first one multiplied by the normal second, and then go u v prime. Normal first function, derivative of the second. So if I differentiate both sides with respect to time, when the exponent on each of the letters is just 1, then the derivative of that will be 1, but then we have to go dA dt. And then what I would do is I would take the derivative of L, so I would do like the u prime, and then we're multiplying by regular v. So what you end up doing, guys, is you multiply by the regular w out front and have dL dt beside it. Just looks a little bit neater than going dL dt times w. And then, so I did the derivative of the first times normal second, and then normal first times the derivative of the second, dW dt, like that. That's how the relationship would look. Okay, so with a triangle, find an equation that relates dA dt, dB dt, and dH dt. The area of a triangle is a half times the base times the height. So the derivative of A is 1 dA dt. And what you can do is leave the 1/2 out front, and then we're going to do the derivative of B. So I'm going to leave the h out front, and then go dB dt plus regular b, and then dH dt. And that's how that relationship would go. Excuse me. Then we can look at some volumes. Volume of a cylinder is pi r squared h. So again, you see two variables there, r and h. Find an equation that relates dV dt, dr dt, and dH dt. So the derivative of v is 1 dV dt. We could leave the pi constant out front if you want, and then do the derivative of this part. So the derivative of r squared is 2r. And then we would put dr dt, and then we have to multiply by regular h. So what you can do is multiply by regular h and then have your dr dt at the end. Okay, so that's doing the derivative of the r variable, leaving h normal. And then we would leave the r variable expression normal and do the derivative of the h one, which is just 1, and then dH dt. Okay, the volume of a cone is 1/3 pi r squared h. Find an equation that relates those three things. So we would have dV dt, and for this one we can leave the constants out front and then do the derivative. The derivative of r squared is 2r dr dt, and then times h. So I'm going to have the multiply by h in front, and then we would have r squared dH dt. Boom. And then for some reason we do a cone here again, treating h as a constant, like if the height of the cone doesn't change, but the radius does, I suppose. Okay, then we could do this situation. Okay, so if h is a constant, then what you can do is differentiate both sides with respect to time. If h is a constant, then it can just come forward with all the other constants. So those are all constants, and then we would just be doing the derivative of r squared, which is 2r dr dt. Okay, so we could do this, and we've got 2 times 1/3 is 2/3, and then we have pi rh dr dt. Okay, let's get on to a sphere. The volume of a sphere is 4/3 pi r cubed. Find an equation that relates dv dt and dr dt. Okay, this one should be pretty easy. We would go 3 times 4/3 pi. 3 times 4/3 is just 4. And then we would still have the pi, and then that would go down to r squared. And then we are differentiating with respect to time, so dr dt. Okay, a rectangular box, the volume is length times width times height. This time we have 3 variables on the right-hand side. Write an equation that relates dv dt, dl dt, dw dt, and dh dt. Okay, and so you'll see an interesting thing that comes out in this formula, guys, but I do like to show where it comes from. What you have to do first is you have to treat this right-hand side sort of as the product of two things, perhaps the L times the WH. So you treat it as two things first, like that, and then if we differentiate both sides with respect to time, the derivative of v is 1, and then dv dt. And what we would do here is we would do the derivative of the L and keep the WH normal. So I'm going to go WH, the derivative of L is dl dt, plus, then we would keep the L normal, and we would do the derivative with respect to time on the WH, but notice that that itself is a product. So we have to do the product rule on this piece. Okay, so it's L times the derivative with respect to time of W times H. So now we're going to have a second line here plus L. Now the derivative with respect to time of W times H, we have to do the product rule on that. So we would do the derivative of the W part. So I'm going to leave H constant and then go dW dt plus, then you leave the W constant, the derivative of H is 1, but then dH dt with respect to time. Okay. Then notice that the L can multiply onto both of these, and we get a final answer of WH times dl dt plus LH times dWt times dW by dt plus L times W, we can go LW dH dt. And if you look at that, each of the letters basically takes a turn with its like derivative form. So you've got WH dl dt, and then it's LH, and the W's turn to be dW dt, and then LW, and then dH dt, H's turn, so to speak. Okay, so that's a nice formula relating those rates of change. Okay, I don't think I want to say anything more about that. That's looking good. Okay, then we can talk about lengths of sides, right triangle. In a right triangle, we can use Pythagoras. A squared plus b squared equals c squared. This is just another form. X squared plus y squared equals z squared. Find an equation that relates dx dt, dy dt, and dz dt. So you just differentiate everything with respect to time. The derivative of x squared is 2x, and then dx dt. The derivative of y squared is 2y, and then dy dt, and the derivative of z squared is 2z times dz dt. Okay, notice that these all have a factor of 2 in common, so we could divide both sides by 2. Sorry, I forgot the y out front here. Okay. Now we'll do a right triangle again here. Find an equation that relates dx dt and dz dt if y is a constant. So this time y is a constant. So when we do the derivative of x squared, that will just be 2x times dx dt. If y is a constant, then y squared would also be a constant, and the derivative of that is 0. So that one would just go away. And we would get then 2z dz dt, and these both share a common factor of 2. Okay, and so we get x dx dt equals z dz dt. And finally, the diagonal of a rectangle. The diagonal is equal to the square root of x squared plus y squared. That again comes from Pythagoras. And I'm just going to do a quick pause here, everyone. Somebody's going by with a lawnmower. Alright, everybody, I'm back. Diagonal of a rectangle. Diagonal equals the square root of x squared plus y squared. Find an equation that relates d dt, dx dt, and dy dt. Okay, so the derivative of d is 1, and then I would go d dt. And remember, when you have the square root of u, the derivative is 1 over 2 root u, like so, and then multiplied by u prime, the derivative of the inside. The derivative of the inside is going to be 2x dx dt plus 2y dy dt. And all of that stuff is kind of like on top of the fraction. Okay, but you notice that there's a factor of 2 on everything up top. So if we were to divide that 2 out, it would cancel with that 2. So here's what we're going to get. d dt is equal to, on the top, we have x dx dt plus y times y dy dt divided by the square root of x squared plus y squared. All right, and a right triangle, tan theta equals y over 100. So that would be a situation like this. got to be a 90-degree triangle to use SOHCAHTOA, and it would be opposite over adjacent, like so. Find an equation that relates d theta dt and dy dt. So as the angle changes, how does y change? Note one side of this triangle is made constant. Yeah, so the 100 is staying constant. The y and the hypotenuse would change. So we differentiate both sides with respect to time. The derivative of tan theta is secant squared theta, d theta dt. And the derivative of y over 100 would be 1 over 100 times dy dt. And there's our derivative. Awesome, so we can get on to a question from 1985 AP exam number 31. And it says the volume of a cone of radius r and height h is given by volume equals 1/3 pi r squared h. If the radius and the height both increase at a constant rate of 1/2 centimeter per second, at what rate in centimeters cubed per second is the volume increasing when the height is 9 centimeters and the radius is 6 centimeters? Okay, so let's draw a cone here. Radius, height, so we'll do our find when given thing, and they say at what rate is the volume increasing? Okay, so we want to find change in volume with respect to time when the height is 9 centimeters. So at the instant that we hit 9 centimeters, and at that same instant, the radius hits 6 centimeters, given the radius and the height both increase at that constant rate, so the change in height with respect to time, so this is the height, this is the radius, is 1/2 centimeter per second, and the change in radius with respect to time is 1/2 centimeter per second. Okay, so of course then we need a formula relating the volume and the radius and the height in a cone, and they've given us that formula. Volume is equal to 1/3 pi r squared h, so we need to differentiate both sides with respect to time. Okay, so I'm just dividing out the constants, and then I'm going to go, hey, the derivative of r squared is 2r. I'm supposed to do dr dt. I'm going to put that multiple of h as well. And then we would get r squared times dh dt. And we're trying to find dv dt, and conveniently it's already by itself. And so let's see if we can just plug in everything we know. We know r and h, and we know dr dt and dh dt, so everything is good. So we'd have 2 times 6 centimeters times 9 centimeters times dr dt is 1/2 centimeter per second plus 6 centimeters squared dh dt is 1/2 centimeter per second, and we get a change in volume with respect to time that is equal to, okay, let's work this out. I'll probably just leave the 1/3 pi for now. Go 2 times 6 times 9 times 1/2 plus 6 squared times a half. That gives us 72. Oh, that's divisible by 3, so be 72 times a third pi. So if I multiply that by 1/3, I'm going to nicely get 24. Okay, and then we still have the times pi. So this is going to work out to 24 pi. And notice centimeters cubed per second. Okay, so now we'll get on to some related rate problems involving distance. Example 1, a taxi drives 3 kilometers east and then turns north, traveling at 50 kilometers per hour. How fast is the distance between the cab and the starting point increasing when the taxi has driven 4 kilometers north? Okay, so let's set up some directions here first. North, east, south, west. And so this taxi drives 3 kilometers east, then turns north, traveling at 50 kilometers per hour. So then they're heading this way, going a y distance at 50 kilometers per hour, and it wants to know how fast is the distance between the cab and the starting point increasing. Okay, so we know that the cab is here. This is the start point. How fast is the distance between the cab and the starting point increasing? So we want to know how quickly this Z piece is increasing when the taxi has driven 4 kilometers north. So they want us to find how fast the distance between the cab and starting point is increasing. So they want us to find change in Z with respect to time when the taxi has driven 4 kilometers north. So at the instant Y hits 4 kilometers, given the taxi is traveling north at 50 kilometers per hour. So the change in Y with respect to time is 50 kilometers per hour. Okay, so now we just need a formula involving, excuse me, y and z. We'll use Pythagoras because it's a 90-degree triangle. So 3 squared plus y squared is equal to z squared. And when we differentiate both sides with respect to time, the derivative of the constant 3 squared will go away. We will get 2y dy dt equals 2z dz dt. And we want to get dz dt by itself. So dz dt is equal to, first of all, we could divide both sides by 2 and that will cancel. We just have to divide both sides by z as well. So we would have y dy dt divided by z. Okay, so y is 4 kilometers. The instant y is 4 kilometers. Dy dt is 50 kilometers per hour. And at the moment we don't know what z is, but we can figure it out because what you do is you solve for z at the instant the y hits 4 kilometers. So we would have 3 kilometers here. Y will hit 4 kilometers at some instant, and then we can figure out z using Pythagoras. Right? So I would go z squared is equal to 3 squared plus 4 squared, so z squared is equal to 9 plus 16, which is 25, so z ends up being 5. Mathematically, we would do the square root thing, plus or minus and all that, but we're finding a distance, so we get z equals 5 kilometers. And so then our change in z with respect to time is equal to 4 times 50 divided by 5, 40 kilometers per hour. See how this kilometers is going to cancel with that, and we will get change in z with respect to time is 40 kilometers per hour. All right, let's try example 2. A bug is walking away from a wall 40 meters high at a rate of 3 meters per minute. At what rate is the distance from the top of the wall changing when it is 30 meters from the wall? Okay. So we have this wall that is 40 meters high, and a bug is walking away from the wall at a rate of 3 meters per minute. Okay, at what rate is the distance from the top of the wall changing when it is 30 meters from the wall? Okay, so at first we have to make the distance the bug is away from the wall variable. And we want to know at what rate is the distance from the top of the wall changing when the bug is 30 meters from the wall. Okay, so find change in distance with respect to time when x is equal to 30 meters, when the bug is 30 meters away, given that the bug is walking away from a wall at 3 meters per minute. So the change in x with respect to time is 3 meters per minute. Okay, so again, this is a Pythagoras type question. A squared plus b squared equals c squared. D is the hypotenuse. So we would have d squared is equal to 40 squared plus x squared. Differentiate both sides with respect to time. Derivative of 40 squared is 0. And we need to get d dt by itself. Divided by 2d. The 2's will cancel. X is equal to 30 meters. dx dt is 3 meters per minute. Divided by, we have to figure out d now that we're talking about the instant x is 30. Right, so this is 40. X is going to hit 30 meters at some instant, and so what is d? D squared is equal to 30 squared plus 40 squared, so we would go 30 squared plus 40 squared. That's what d squared is equal to, and so then d will be the square root of that. D will equal 50 meters. So I'll put 50 meters here, and our change in distance with respect to time then is 30 times 3, divide that by 50, fraction that if you want. 9/5 meters per minute. Okay, so there's example 2. Example 3 says a right triangle has a hypotenuse of constant length 10 centimeters. One leg of the triangle increases at a rate of 2 centimeters per second. When it is 6 centimeters long, what is the rate at which the other leg is decreasing? Okay. It has a hypotenuse of constant length 10 centimeters. And let's do our find when given thing. And let's say guys that the y leg is increasing, so that we're bringing this point down like that, and then the hypotenuse stretches out more like this so that the x increases. Okay, let's find how y is changing with respect to time when x is equal to 6 centimeters given one leg of the triangle increases at a rate of 2 centimeters per second. I made that my x length. The change in x with respect to time is 2 centimeters per second. Okay, and so then when we hit that instant of x being 6 centimeters, how quickly is length y decreasing, basically, is what it's asking. Okay, so we have to relate x and y. So we can go x squared plus y squared equals 10 squared. Differentiate both sides with respect to time. Oops. The derivative of 10 squared is 0. And we want to get dy dt by itself. So dy dt is going to equal negative 2x dx by dt. So I would subtract this whole term over, and then I have to divide by 2y. So dy dt is going to equal negative x times dx dt divided by y. Okay, at the instant that x hits 6 centimeters. So we will have negative, and then 6 centimeters times the dx dt is 2 centimeters per second, divided by, when x is 6, we would have y squared plus 6 squared equals 10 squared. So y squared plus 36 equals 100. So y squared equals 64, so y is equal to plus or minus square root of 64 plus or minus 8. It's a length, so y equals 8 centimeters. And so the change in y with respect to time is equal to -6 times 2 divided by 8, and we get -1.5 as a fraction. It's -3/2. And that is going to be centimeters per second. Okay, and the negative means that that length is decreasing in size. So -3/2, so you're losing 1.5 centimeters per second. Okay. All right, and so that is example 3. Okay, example 4 says, a ladder 13 meters long is resting flat against a building. The bottom of the ladder is being pulled along the ground at a constant rate of 3 meters per minute. How fast is the top of the ladder decreasing after 4 minutes? Okay. Okay, so here's the building. And imagine this red ladder like this, and what we're going to do is we're going to pull that point out. And as you pull that point out to here, it's going to cause this point to come down so that your ladder goes like this. Okay, and so it's a 13-meter ladder. The bottom of the ladder is being pulled along the ground at a constant rate of 3 meters per minute, so let's call that our x length. And so that's our given, that the change in x with respect to time is 3 meters per minute. And it wants to know how fast is the height of the top of the ladder decreasing after 4 minutes. Okay, so it wants us to find the change in y with respect to time. When? Okay, this question is a little bit different. After 4 minutes, so when we hit a time this time of 4 minutes, how are we going to incorporate that into x and y? So there's our 90-degree triangle. Okay, and so the height of the top of the ladder is decreasing, so we should get a negative dy dt for this. Okay, so we have to relate x and y in an, and it's in a 90-degree triangle, so x squared plus y squared equals 13 squared. Differentiate both sides with respect to time. Derivative of 13 squared is 0. And we need to get dy dt by itself again. We would have negative 2x dx dt over there. right? Taking this whole term, subtracting it over, and then we're going to have to divide by 2y, so that'll knock off the 2's for us. So we will have negative. Ooh, we have to figure out what x is after 4 minutes. Okay? And then subsequently what y is. So the change in x with respect to time is 3 meters per minute. So the x distance will be the rate of change times the number of minutes, times 4 minutes. Minutes will cancel, we'll be left with 12 meters. Okay, so the x is 12 meters. dx dt is 3 meters per minute divided by what's y. So now we have a triangle where this is 13. We know the x is 12, so then what's the y? And we can do Pythagoras to get y. Y squared plus 12 squared equals 13 squared. So y squared equals 13 squared minus 12 squared. So y squared equals 13 squared minus 12 squared, which is 25. Awesome. So mathematically speaking, something squared equals 25. Plus or minus 5 could work, but the context of the question dictates that this should be positive 5 meters, like that. And so our change in y with respect to time is equal to negative 12 times 3. Divide that by 5. We get negative 7.2, math, fraction if you want, negative 36 over 5 meters per minute. So you can see that meters will cancel with that one. We'll just be left with meters per minute. And it makes sense again that that's negative because that y height is decreasing. All right, so there's example 4, everybody. Okay, we're almost there. It looks like 3 more examples here. So example 5 says a police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Okay, set up some directions: north, east, south, and west. Okay, so we could kind of get fancy about doing a diagram too, right? And show this is the road situation. Okay, so a police cruiser approaching a right-angled intersection from the north is chasing a speeding car. So the cruiser's coming down like this. It's chasing a speeding car that has turned the corner and is now moving straight east. Okay, so this is the car and this is the police. Okay, when the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. Okay, and so here's what we're going to have to do ultimately, guys. We set up a triangle like this. They're talking about this straight line distance increasing. And this is the y distance that the police would have to go and the x distance that the car is going. Okay. Okay, and the ultimate question is, what is the speed of the car? So they want us to find the change in x with respect to time when the cruiser is 0.6 miles north, so y is 0.6 miles, and the car is 0.8 miles to the east, so x is 0.8 miles. And what are we given? We are given at a certain instant that the change in distance between the two cars with respect to time is 20 miles per hour. And the police cruiser is moving at 60 miles per hour, so the change in y with respect to time is 60 miles per hour. And is that everything we know? I think so. Okay, so now we have to relate x and y and d, and this of course is a 90-degree triangle. So x squared plus y squared equals d squared. Differentiate both sides with respect to time. And we want to get dx dt by itself. Okay. So dx dt is going to equal 2d dd dt minus 2y dy dt. So I'm taking this and subtracting it over, and then I'm going to divide by 2x. Divide by 2x like that. Okay, and so we can cancel out those 2's. Change in x with respect to time is, we are going to need to figure out this d. We know at a certain instant y is 0.6 miles, x is 0.8 miles, so then we can get the d, doing Pythagoras, right? So if this is 0.6 and this is 0.8, what is d? And we would use a quick Pythagoras on that, right? So d squared is equal to 0.6 squared plus 0.8 squared. There's d squared. Oh, nice. So the square root of d squared is 1. So d is equal to 1 at this instant. So we're going to have 1 times dd dt which is 20 miles per hour minus, what's the y? 0.6, and dy dt is 60 miles per hour, all divided by x, which is 0.8 miles. Okay, so dx dt is 1 times 20 is 20, minus 0.6 times 60 is that, divided by 0.8. Oh, I made a little mistake here. Alright, I made a small little mistake, an oversight, which is this. Most of the top is right, it's just, here's the thing that's going to change. D is 1, dt is 20 miles per hour, minus the y is 0.6 miles, and the change in y with respect to time is actually negative 60 miles per hour, and we have to make that negative because this y distance is decreasing. So that's a small little thing that has big implications. That's actually negative 60 miles per hour because it's decreasing that y. And the change in x with respect to time is positive because that x distance is increasing. Okay, so we should get a positive answer. 20 minus 0.6 times negative 60. Divide that by 0.8. There we go. dx dt is 70 miles per hour. Alright, let's try example 7. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Okay, so we've got this rangefinder, hot air balloon. And we have this angle theta, we could call it, changing. There's our 90 degrees. There's the height of the hot air balloon, which is changing. We do know that this is 500 feet away, though. So find how fast is the balloon rising at that moment, the change in y with respect to time. When theta is equal to pi over 4, given the angle is increasing at the rate of 0.14 radians per minute. So the change in theta with respect to time is 0.14 radians per minute. Okay, so we need an equation involving theta and y, 90-degree triangle. This is the opposite side, and across from the 90 is the hypotenuse, so this is the adjacent. Opposite and adjacent comes from tan, so tan theta is equal to y over 500. And then differentiate both sides with respect to time. Derivative of tan theta is secant squared theta. d theta dt equals, the derivative of y is 1. Got 1 over 500 times dy dt, and we want to get dy dt by itself, so we would multiply both sides by 500, so we would have 500 secant squared. We want the height, the instant the angle is pi over 4, which is 45 degrees. times, by the way, and then times d theta dt 0.14. radians per minute. Okay, so how are we going to do secant squared pi over 4? Mode, I'm just going to make sure I'm in radian mode because the angle is in radian measure. Secant is just 1 over cos. So we'll have 1 over cos of pi over 4, but it's secant squared, so we're going to have to square this whole big thing as well. So I'm going to put brackets around all of it. That is secant of pi over 4. And so squared would be like that. And then we're going to go times 500 and times 0.14. Okay, and we get 140. Feet per minute. Okay, the 500 was in feet. All right, so there's example 7, and for some reason there was no example 6, just jumped from 5 to 7. No explanation for that, really. Okay. Let's try example 8. So a man is walking away from a street light at a rate of 5 feet per second. If the man is 6 feet tall and the light is 15 feet high, how fast is the man's shadow lengthening when he is 10 feet from the base of the street light? Okay. There's the street light, 15 feet high. We have the man. He is 6 feet tall. The man is walking away from a street light at a rate of 5 feet per second. So we could do this. Call that x. So here's what we are given so far, that change in x with respect to time is 5 feet per second. The man is 6 feet tall, the light is 15 feet high. How fast is the man's shadow lengthening? Okay, so light beams are going to come down like this. Okay, and they get blocked by his body and his head, and the ones that make it over his head cast a shadow here. Okay, and so there's the shadow. And the more he moves away from the light, the sharper the angle will be of the light beams, and it will create a longer shadow. So we can call the length of the shadow L. How fast is the man's shadow lengthening? So it wants us to find the change in shadow length with respect to time. When he is 10 feet from the base of the street light, so when x is equal to 10 feet. Okay, and so our problem here is we have to come up with some sort of equation that relates x and L. Okay, and for this, guys, we are going to have to use similar triangles. Notice that there is a small 90-degree triangle right here, and then there is this large 90-degree triangle here. Okay. Okay, they both have a 90-degree angle. They have this angle in common, which forces this angle to equal this angle. Okay, and so these are similar triangles. They have equal angles. Okay, and when you have similar triangles, their sides are proportional. Okay, which means the bigger triangle is just a multiple of the smaller triangle. So this is L and this is 6 in the small triangle, and in the big triangle we've got x and L, so this is x plus L, and this is 15. So the equation is this. L divided by 6 is equal to x plus L divided by 15. Okay, so there's our equation that involves x and L. We can simplify it a little bit before we differentiate both sides with respect to time, so why don't we cross multiply? We would get 15L equals 6x plus 6L. Subtract 6L from both sides and we get 9L equals 6x. Differentiate both sides with respect to time. The derivative of 9L is 9, dl dt. The derivative of 6x is 6, dx dt. What are we trying to solve for? This guy. Divide both sides by 9. So we will get 6 over 9 times dx dt, which is 6 over 9 times the dx dt is 5 feet per second. Okay, so we end up with 6 times 5 divided by 9. If we fraction that, 10 over 3. Over 3 feet per second, okay, is the amount that the shadow is lengthening. Change in shadow length with respect to time. Alright, so there you go, guys. Those are the 4.6b notes, which is more on related rates, and this assignment looks pretty good. I changed from 1 to 7 all to odd. I've axed number 9. Of course, you can try any questions you want. I axed 22 and 24, 31 and 34, but then I did add in 33. And remember, I do have my handwritten answer key on my website, kamosi.yolasite.com. And then there's this question from the 1991 AP exam, if you want to give that a try. I could give you the answers to these right now, just as straight answers. Should get 20 over 7 feet per second for this one. This one ends up being 35 feet. And this one here ends up being 35 over 8 feet per second, or if you want to write it as a decimal, 4.375 feet per second. So I'll just give you the answers to those for now, see if you can get them. If you want me to do a video showing how to do this question, please just let me know. Okay, so there you go, guys. That's the end of 4.6, and that's actually the last section in this applications of derivatives. So next week I'll probably send you a couple practice quizzes, and then, you know what, I might even send you the unit test as well that you can do open book and then send back to me for marks. Alright, everybody, I will talk to you soon.